Now, another type of structure we have is spinel structure, fourth type. Spinal structure. Write down spinal structures are the examples of ionic crystal. Spinal structures are the examples of ionic crystal with more than two types of ions. Spinal structures are the examples of ionic crystals with more than two types of ions. These are the compounds of two different cations. These are the compounds of two different cations. In bracket you write down A2 plus means we'll have a divalent cation and we'll have a trivalent cation. A2 plus and B3 plus. Right? Are the compounds of two different cations, A2 plus and B3 plus, and oxide ion. Right? O2 minus ion. The general formula for this type of structure we have A, B2 and O4 type. A, B2, O4 type. Right, now further, this spinal structure also have two different types here. So in this one, the first type you write down in spinal structure, we call it as normal spinal structure, and the second one is inverse spinal structure. Normal spinal structure. Now, in this, the important point, again the same, position of anions and cations here. So in inverse spinel, what happens? O2 minus has FCC packing or CCP packing. Next point, 1 by 8 of tetrahedral voids are occupied by divalent metal ion, that is A2 plus we are assuming here, divalent metal ion, and half of the OVs, octahedral voids, are occupied by trivalent ion, that is B3 plus. Okay, so could you tell me how many A plus we have? How many A plus, how many B plus we have? Sorry, A2 plus and B3 plus?
1 A2 plus.
Number of A2 plus is what?
1.
1 by 8 into 1. Sorry, 1 by 8 into 8, that is equals to
1.
1. 1 second. 1 by 8. So number of tetrahedral void is 1. Number of B3 plus equals to number of octahedral void is 4, right? And half of the octahedral void has been occupied. So it is 2. Could you tell me for O2 minus?
4.
Number of O2 minus is nothing but FCC packing, so it is 4. So look at the ratio here. What is the formula? The formula is A B2 O4. That is the general formula here. Okay, A B2 O4. This is the normal spinal structure. Now you have this information that how many octahedral void is vacant and how many octahedral void is occupied. Similarly, for tetrahedral void, you have the information, right? So they can ask you any question on this. Let me just give you a few examples here. For example, if I ask you the ratio of TV divided by OV occupied in spinal structure, and when I write a spinal structure, it means it is normal spinal structure. Could you tell me the answer here? How many tetrahedral voids are occupied? 1, right? See, number of A2 plus is 1 by 8 into 8. 1 by 8 of the tetrahedral void is occupied. So one tetrahedral void is occupied, and the number of octahedral void occupied is 2. So it is 1 by 2. Okay. They can also ask you TV by OV unoccupied in this. TV by OV unoccupied. That would be 7 by 2, right? 7 is unoccupied, and out of 4, 2 is occupied. So 2 is unoccupied, 7 by 2 is the answer. So all these questions are not tough, just need to have this information, that is it. Done? Okay. The second type of structure we have in this spinal structure, we call it as inverse spinal structure, B. Inverse spinal structure. Okay, write down. Here also you see O2 minus, we have no change. O2 minus forms FCC packing. FCC packing. A2 plus the divalent cation. This is also same. 1 by 8 of TVs, tetrahedral void. But we have a difference in the position of trivalent ion. Okay, it says that it is present in 1 by 8 of TVs plus 1 by 4 of OV. Means this trivalent ion is present in both tetrahedral void and octahedral void. If you copy this down, one sec. Done? Okay. So for number of O2 minus, again you see here, is 4. Number of A2 plus is 1 by 8 into 8. That is 1. Number of B3 plus 1 by 8 into 8 plus 1 by 4 into 4, and that is 2. Okay. And hence for this also, the molecular formula is A B2O4, but the arrangement of ions, trivalent ions here, is different. Tell me, OV by TV, occupied, OV by TV, unoccupied. What is the value? Yes. What is the answer? Two in both. Yes. So number of OV occupied here is we have only one octahedral void occupied, right? 1 by 2, no? Is it?
Yes, sir, 1 by 2 for both.
Yeah, it's 1 by 2. 1 OV occupied and 2 TV. 1 TV is taken up by the trivalent ion and other one is divalent ion, right? Yeah. So 1 by 2 here, and similarly here also 1, and we have 2. 1 by 2. Take care of this thing in the question what they have asked. Have they asked for TV by OV or OV by TV? Okay, take care of that. They can frame any questions from this. Okay, they can even mix inverse spinel and normal spinel structure also. Okay, so take care of that. Another type of structure after this spinel, write down. See, the example of this is inverse spinal is Fe3O4. Fe3O4, remember we have done this in the 11th grade. We have two types of oxidation state of ion here, right? What is that? Fe2 plus and Fe3 plus. Right. So one is divalent cation, Fe2 plus, FeO dot Fe2O3. So this is arranged in inverse spinal manner only, inverse spinal structure. Okay. Yeah. Next, write down corundum structure. One, two, three, four type, no? Corundum. The general formula of this type for this type of a structure is A2O3 type. A2O3 type. Very common one, you know, it is Al2O3. Example you see. We have Al2O3. We have another structure of F, example is Fe2O3, the oxides of iron you see. The previous one is Fe3O4, another oxides of iron has inverse spinel structure, but this one has corundum structure. Okay, Cr2O3 also has corundum structure. Okay, write down. In this, the oxide ion that you have, O2 minus, it forms HCP arrangement. HCP arrangement. A3 plus present in 2/3 of octahedral voids. 2/3 of octahedral voids. And general formula is A2O3. You can find out the number of A3 plus and O2 minus ion. You will have the same formula. So see here, 2/3 of octahedral void. HCP arrangement. What is the rank of this? Is it 6, right?
Yes, sir.
So oxygen is 6 and 2/3 of this OVs. We know the number of OVs is nothing but the rank of the crystal unit cell. So total number of OVs are also 6. Total number of TVs are 6 into 2, 12. So here we have 6 OVs. So out of 6, 2/3 is occupied. So 2/3 into 6, that is 4. Right? So we have A4O6, that is A2O3 type structure. Clear?
So actually in the woodsite structure, there, why did we take it as 4? Even there it should be 6, right?
Let me check. This is the coordination number 4 I have taken.
Okay.
I have written the rank of this thing, unit cell. It is the coordination number.
Yes, sir. Yes.
Yeah. Yeah. So this is the corundum structure. This is also important. One last one I write down, the structure of FeO, another oxides of iron, the structure of FeO. After this, we have one more, that is the diamond, structure of diamond. Structure of FeO and then diamond we'll see. Write down. Again here, O2 minus forms CCP packing. In all these you see the anions occupy the lattice points, right? And cations occupies the void. Okay, that's a general thing you can now understand here. O2 minus forms CCP packing and Fe2 plus occupies all octahedral voids. All octahedral void. It's looks like NaCl type structure only. Okay. But write down, this oxide is found to be non-stoichiometric. But this oxide is found to be non-stoichiometric. with the formula Fe 0.95 and O. This molecule, we call it as wustide, W-U-S-T-I-D-E, wustide. Okay, non-stoichiometric compound. This is the formula we have. Right now, in this type, some of the Fe2 plus ion, divalent ion, some of the Fe2 plus ion in octahedral void are replaced by Fe3 plus ion Fe3 plus ion and every 3 Fe2 plus ion and every 3 Fe2 plus ion would be replaced by every 3 Fe2 plus, every 3 Fe2 plus ion would be replaced by 2 Fe3 plus ion in order to maintain electrical neutrality. Right? In order to maintain electrical neutrality. Just this point you have to memorize. So what happens in this, you see, to maintain the electrical neutrality of the crystal, 3 Fe2 plus ion is replaced by 2 Fe3 plus ion so that the charge will be balanced. But in this way, what happens? 3 ion atom is replaced by 2 ion atom, right? That's why the system or the crystal becomes Fe or ion deficient crystal. Okay? If you see the number of atoms, then the crystal becomes ion deficient crystal. Okay? And the last structure we have in this, write down a structure of diamond. Once they have asked question on this, the packing efficiency of diamond. Okay. The last one, write down the structure of diamond. Write down. Diamonds has FCC structure. It has FCC structure. But along with this, there are 4 more atoms present. So FCC structure with 4 more atoms are present in alternate TVs, alternate tetrahedral void. Tetrahedral void. Okay. So the number of carbon atom in diamond, if you see, the number of atoms or the rank if you count here. For FCC it is 1 by, FCC it is 4, so half into 6 plus 8 into 1 by 8. But along with this, 4 atoms present in the tetrahedral void. So the number of atoms or the rank is 8 over here. The carbon atom, write down next. Write down. The carbon atom in tetrahedral void, in tetrahedral void is in contact with its 4 surrounding carbon atoms. Its 4 surrounding carbon atoms. Hence the coordination number is 4. Right? Carbon atoms present in tetrahedral void is in contact with its 4 other nearest carbon atom. Coordination number is 4. Next point, the carbon atom in FCC lattice, the carbon atom in FCC lattice do not touch each other. Right? If you look at the distance, so the tetrahedral void and the corner atom, the distance is root 3a by 4. So the relation of A is 2r is equals to root 3a, the body diagonal, and 1/4 of it is root 3a by 4. So the tetrahedral void, the corner atoms and the tetrahedral voids are in contact, and this is the face center atom. We have 3 face center atom, right? In the cube, if you see, have discussed last class also. So this is the relation of A and R for this thing. For diamond we have, okay? Packing fraction you can find out easily. The packing fraction is, Z effective is 8. So we'll write down 8 into 4 by 3 pi r cube divided by A cube. A and R relation you already have, you substitute it, and the answer that you get is 34%. So once they have asked this question, that what is the packing fraction of diamond? Okay, it's 34%. You can memorize this also. Otherwise, position of atoms, if you know, you can calculate this easily.
So, but why did you say it doesn't touch each other, the FCC lattice?
In FCC lattice, normally what happens, the atoms are in contact, right? The face center and means along the body, along the face diagonal, if you see.
Yes, so 4 are equal to.
But in case of diamond, the case is different. The carbon atom is present at a tetrahedral void, and here the space is not that much. So it, because of the presence of this atom, the corner atoms and the face center atoms loses its contact. Okay. So these 2 corner atoms and the tetrahedral voids are in contact. These 2 are in contact. Okay. Here also in contact, and here also it is in contact. This one and this one in contact. But this atom is not in touch with this. See, all these, the thing we have, it depends upon the radius of the atoms. It's very difficult to explain this theoretically. Okay. It depends upon the radius of the atom, that how, depending upon the radius, we can have the distance over here. Right, and hence we can say geometrically that whether these are in touch or not. Okay, so in case of carbon atom, what happens? The placement of carbon atoms in the tetrahedral void, because of this only these 2 atoms loses its contact. That's why the carbon atom, the diamond, the structure of diamond is a bit different with the normal FCC lattice that we have. And we have this relation of A and R because of this. How do we get to know this structure? For that, we have different crystallographic system by which we can find out. One of the method we have that we use is Bragg's law, right? That we'll discuss in the last. We use to determine the interplanar distance between the two layers in the structure. So there are various techniques by which we can find out the structure of the crystal. So with that only, we define the atoms or the structure of any crystal like we are discussing all this. Okay, so logic, if you ask me, so why it is not in touch, I don't have much to say, frankly speaking. The only reason is if the space here is not that enough, then this will, like we have in CSCl, the body center atom push the outer atoms, right? And hence the atoms loses contact. So in diamond, it does not have the normal structure like we have FCC. These are not in contact, the face center and the corner atoms. But all the face center and corner atoms with the atoms which is present in tetrahedral void, they are in touch with it.
Yes, sir.
Okay, so all these things you see, whatever I have discussed so far, I have just given you the information. Right? It's not like I'm not teaching anything to you, but this is the information. You should know the position of cations and anions. That is it. And how do we get these positions? By all those crystallographic techniques that we have, by which we can, look at the structure of various crystals and define. Okay, so based on those studies, these structures are given. So these are the structures we have discussed, all important one. Apart from this, we have few more structures, but that haven't they asked in the exam. It's not given in the syllabus also. So I'm not taking up those things. Now you look at this question, which I was discussing initially. This one you try. Yes. So what is the answer you are getting? All of you are getting A.
Yes, sir.
Yeah, A is correct. The question is, in a solid having rock salt structure, if all the atoms touching one body diagonal plane are removed except the body center, then the formula left in the unit cell. Okay. So all the atoms touching one body diagonal plane are removed. So which plane it is talking about?
The plane in that other question.
The same plane, right? From the
Yes.
top edge and the diagonally opposite bottom edge, right? So along this edge, if you remove, so we are removing uh, 4 cornered atoms. 4 cornered atoms we are removing. 2 edge center atom we are removing. That is it, right? Except the body center. Okay. So 4 cornered atoms.
The two face also.
Hmm?
The
Yes.
two face of them.
Face also. 2 face center. Side, adjacent polar face, side polar face, right? 2 face center also we are removing. Okay. Fine. So A is, it's not given, A is at the face center, forming the face center, it's not given. So which atom you assume at the face center? FCC arrangement?
The B.
B you have.
When it's rock salt.
Okay. Fine. So the contribution of B is what? We have only 4 cornered atoms, so 4 into 1 by 8. And we have 4 face center atoms, so 4 into 1 by 2. So 2 plus 1, we have 5 by 2 it is. And A in the octahedral void. So A is, we have 2 octahedral voids, so we have 12 edge centers, so 10 into 1 by 4 plus 1. So 5 by 2 plus 1, so it is 7 by. Is it right? So we are getting A7, D5, which is A. A7, B5, the ratio is that only A. So this is the one we have. Second one you see, this is structure. Done? 346 you are getting? CSCl has BCC arrangements. Along the Boy diagonal, it is in touch. So we have 2R plus 2R minus is equals to root 3A. Interionic distance. Which ion you are considering? CS and Cl. CS plus and Cl minus, is it? Or 2Cl minus? I think
Yes.
Yes, and C.
because 2Cl minus, the distance is what? Either we can have root 2A by 2 or A only, because position of Cl minus is what? It is at the, it is at the corner only. BCC we have, no. Between 2Cl minus, the edge length is A only, correct? That is the value of the edge length of the unit cell. So obviously the question is about CS plus and Cl minus. So we need to find out root 3A by 2, isn't it?
Yes, sir.
Yes, A value is given. You can find out simply root 3A by 2. These are not difficult. Not difficult once you know the structure. If you do not know the structure of CSCl, you won't be able to do it. Okay. One more question I'll show you here. This one. Try this. So for this one, the answer is let's try this. I'm coming. One second. Yeah, done. A2, B2, O3. Yeah, that's right. Ruchir, now you got it right. Ruchir Parekh, I think you are missing something. You check your calculation. The answer is AbO3, Pradyut. See, the crystal should be neutral, right? A and B will have same AbO3. So we can have we'll have various possibilities. For part B, yes, A plus B should be 6, and then you can write down the possibilities that we have. That is it, yeah. So how many different possibilities? Yeah, that's right, Pradyut. How many different possibilities we have? Five. Yeah. So so O2 minus is arranged in CCP. So number of O2 minus, I'll write down directly, is 4. 1/6 of the tetrahedral voids are occupied by cations. Okay. So cation A. So number of A, we don't know the charge on A, right? 1/6 of the tetrahedral void. So it would be 4 into 1/6. A tetrahedral void we have. So we have 8. So we have 8 into 1/6. That is 4/3. And for B, it is 4 into 1/3. That is again 4/3. And hence the formula is A 4/3, B 4/3, O 4. Right, so it is AbO3 type crystal we have here. AbO3 type crystal we have. Now you see we have oxide O2 minus, total negative charge is 6 here. Right? Total negative charge is 6. So whatever the charge on A, suppose A will have plus A we assume, and B will have plus B, and O we all know it is -2, 3 times. So obviously A plus B should be 6, then only the molecule should be neutral, the crystal will be neutral. So we can have various possibilities. We can have A value as +1, B as +5, that is one possibility. We can have A as +2, B as +4, another possibilities. A as +3, B as +3, another possibilities. A as +4, B as +2, and the last one is A we can take as +5 and B +1. So there are 5 possibilities we have. We can have any one of the two, one of the combinations given in the question, right? Here the answer we can write any one of the things. Now in this, till now they haven't asked, but they can ask you numerical value question on this. There are a number of possible, the charges, the possible charges on A and B, so that the crystal is this we have. So suppose this question is an integer type, then the answer for the second part would be 5. Okay, so they can frame questions from this, the integer type one. Okay. Done. Now the last two things we have to discuss in this chapter. The first one is the imperfection in solids, right? And then the second one is Bragg's law. Okay, imperfection we have different types. Completely theory. Okay, just you need to know 2 things. Mainly they ask in imperfection of solids, that is Schottky defect and Frankel defect. Okay, so we'll discuss that only. Before that, we'll start Bragg's law. Okay, so next heading you write down Bragg's law. So we have 552. We'll do the